This paper presents a new approach for CNN inference on pixel process array cameras. These new sensors embed processing and memory into each pixel element, allowing visual data to be immediately processed as it is captured. In this work we show how a CNN can be performed entirely on sensor with no external processing, demonstrating a digit classification network. The key idea behind our approach is storing the network weights directly in the pixel elements rather than in instructions sent to the array. This approach allows many different convolutions to be formed simultaneously in parallel across the processing array, followed by ReLU and max pooling, as can be seen in examples here. Here we see a convolution being performed upon one part of the array. Due to resource limitations, each processing element cannot hold a complete set of filter weights. Instead, these are stored across processing elements and must be copied across to others during execution. Storing the filter weights in pixels in this manner allows us to send one single set of instructions but get many different convolution results spread across the array. The max pooled activation data resulting from a convolutional layer can then be used to perform a fully connected layer. Here we see the weights for the fully connected layer, with the weights for each digit interweaved with one another. Here we highlight the weights associated with the digit 0, the digit 1, 2, and so on. Multiplication of the fully connected weights by the max pooled activation data of the previous layer can be performed in parallel. The values associated with each output neuron can then be summed in parallel to give the output of the network, as can be seen here for this MNIST example. To perform additional convolutional layers, first the output of the previous layer is duplicated using digital operations to avoid analog corruption. Such further convolutional layers can then be executed by sending the array the same set of instructions used to execute the initial convolutional layer. Here we see an example of a second convolutional layer performing 256 different convolutions. The convolutions from such further layers are then combined together to form feature maps, as can be seen here. The resulting feature maps are then duplicated to fill the entire array again, to leave no unused processing element. A fully connected layer can then be performed directly upon these feature maps. However, the layout of these fully connected weights is different than if the previous layer had performed max pooling. In this MNIST network example, by highlighting the weights associated with each digit, we can see they are no longer interweaved in the same way they were when max pooling was performed. Once again, parallel multiplication can be performed between these fully connected weights and the feature maps. Summing the correct pixel values then generates the final neuron activations of the network. Here we show some additional classification examples on unseen data, with the PPA extracting the digit from the initial image, duplicating it across the array, and then running it through the network. As network inference is performed entirely at the point of light capture, minimal data needs to be transferred off sensor, saving significant power and time, and allowing inference over 3000 frames per second. PPA devices are still in the early stages of development, limiting the size of networks that can currently be embedded. However, future devices with greater processing speed and memory per pixel should allow the approach presented here to be applied to deeper networks performing more complex tasks.